Hi, here we discuss about a project, a configurable floating point fused multiple add design with a mixed precision for AI Accelerator. So this work presents a configurable floating point fused multiple add architecture that supports a multiple and mixed precision operations for efficient implementations in artificial intelligence accelerators and high performance computing systems. The proposed designs address these limitations of conventional fixed precision FMA architectures by enabling a dynamic configurability of exponent and mantissa with supporting a range of floating point formats such as a FP32, FP16 and BFLoat16 and DLFloat16 and custom 8-bit types. So this architecture operates in both multi-precision and mixed precision modes, allowing a parallel executions of several low precision FMA or the accumulations of low precision dot product into the higher precision output to enhance the numerical accuracy. A unified multiplayer, configurable alignment and normalized shifter and the optimized dual adder structures are employed to reduce the hardware redundancy, area and latency. The fused arithmetic path minimizes the rounding errors by performing a single rounding operations after accumulations and significantly improving precisions compared to the traditional multiple then add unit. This work synthesized in FPGA and achieves a lower latency and high throughput with reduced power consumptions in silicon area. Compared to the conventional design of IEEE standard 754 format of FMA implementations, the proposed unit achieves up to 35 to 40% of reductions in hardware realizations and 25% improvement in computation speed while maintaining a full subnormal and overflow handling. So this configurables and power efficient designs provides a scalable arithmetic solutions and suitable for the next generation AI accelerators and edge computing and reconfigurable system on chip architectures requiring a high performance mixed precision computations. Now we can verify the work. So this work is fully designed for the fused floating point multiplications. So here what's the core of this work means? This work it will be mixed with the multi-precisions and mixed precision mode. Also it will be come with the 3 operand technique. So here the architectures presents with in the paper. So this one is the existing architectures, the figure 1, the conventional 3-stage FMA design. So this one also will be come with a 3 operand technique. So this is a traditional architectures, which means the existing method. So initially they will be used 3 stages of this architecture. So the first stage comes with the bias generator, exponent alignment control and addend alignment and both multiplications, and the next stage comes with the incrementer and the CSA adders, LSZA, CSLA and some multiplications, and the third stage comes with a normalization, rounding and exponent adjuster, and finally we taken as a sine, exponent and mantissa extractor. So this is a traditional design, but to overcome some problems, this designs it will be modified for accuracy and it will be updated in the next architecture. So this is the next architecture, the figure 3, the proposed fully pipelined FMA designs. The gray text on the right refers is the main stage of the calculation, and purple box is the same similar to the conventional design of the figure 1. And the blue blocks required the proposed design to support a mixed precision operations. So the priority of this work to combine with the mode. So it will become with a mixed precision mode and multi precision mode. So here the multi precision mode it will be working as a normal multiplications. So this one is a 64-bit floating point multiplication. So here the exponent and mantissa its splitting size is a sine bit it will be taken for 4-bit and exponent size it will be taken for 32-bit and mantissa size it will be taken for 24-bit. In between the subnormal flag it will be used for 4-bit operations. So why this mixed precisions and multi precision operations? So they will be controlling this precision level with support of this PRA and PRM, EWA and EWM. So this EWA and EWM it will be controlling the exponent precision, and PRA and PRM it will be controlling the mantissa precision. So it depends upon the PRA. So if it is come with a 00 means it will be 8-bit precision, 01 means it will become with 16-bit precision, and 10 means it will become with 32-bit precision. Okay, so based upon this precision level, we have controlling the internal architectures. Okay, so here the precision mainly focused on to split the bits. Okay, so here the exponent alignment also, it will be split the bit of this 32. Okay, so here 32, it will be divided into 4 numbers. Okay, so 32 divided by 4 means it will become with the 8-bit operations. Also the mantissa, it will become with a 24-bit. So 24 divided by 4 means it will become with a 6-bit operations. Okay, so for that thing, here they are given multiplications operations, the overview of multiplication operations for different precision: 8-bit precision, 16-bit and 32-bit precision. Okay, so for 8-bit precision, they'll be used for different 6 cross 6 operations for multiplications. Okay, so they are not used all the partial product in this area. Okay, they'll be used for LSB and MSB of the partial product, and in between they'll be taken as a partial product from the center of the area. Okay, and the 16-bit precisions, it will become with the LSB 12 cross 12 and MSB 12 cross 12. Okay, and 32-bit precisions, it will become with the 24 cross 24. It will be used for whole partial product size. Okay, so that is a precision level it will be occur here, but this one is not a bit size. Okay, so this the precision is, it will be come with the same size of the floating point multiplication. So only thing is, we need to change this precision level. As per the precision level, we can possible to analyze the different output precision level. So here we can analyze the core of the work. Okay, so here it will be start with A, B, C. Okay, so after the configurable, normal, mixed precision, sine, exponent and mantissa unified extractors, it will be split the data. Okay, after that we need to start with the sine bit. Okay, so the sine bit, it will be work as a normal floating point multiplication which using a XOR operations. Okay, and the exponent, so exponent, it will become with a bias generator. So bias generators, it depends upon the subnormal flag. Okay, so it depends upon the subnormal flag, as well as we need to give a priority to the PRA and EA and EAM. Okay, so to control the bias. Okay, so it depends upon the bias value, the exponent, it will be added. Okay, so once we splitted the exponent value in 4 different level. Okay, so then we need to add the value with a bias. Okay, so which means, so the exponent unbiased values. Okay, so it will be add with EB plus EC minus bias BC minus LZ sum and minus offset. Okay, so this is a biased for product level, and this is for addend level. Okay, so EA minus bias A. Okay, so this bias values, it will be taken with a 7, 15, 31, 63, 127. Okay, so with using this bias, we have different lanes here. So this lanes, as per the priority of PRA and PRM, we need to add this bias values. After that, we need to go with the alignment process. Okay, so here in between we need to calculate the offset value, but the offset architectures, they are not given in this architecture, so we need to additionally include that. Okay, so then only we will get a proper output. Okay, so exponent proposed unbiased values EB plus EC minus bias and LZC. Okay, so here LZC. Okay, so that is a leading zero count. Okay, so here the zero detections passes. Okay, so it will be taken from the mantissa B and mantissa C. Okay, so it will protect the highest bit of the mantissa B and mantissa C. Okay, and to avoid the number of zeros. Okay, so once it will be find out, so then we will be add the values. Okay, and then the value, it will be given to the exponent alignment controller. Okay, so this exponent alignment controller, it will add the value and the finding the maximum value of the exponent biased and exponent biased A. Okay, so A line. Okay, and after that it will be compared, then it will be select the label. Okay, so which using this multiplexes. Okay, so finally we will get a LZC and the alignment amount finalizer. Similarly, we taken a multiple precision booth multiplication output. Okay, for the stage 2 operation. So here the stage 2, it will come with the alignment amount finalizer and addend alignment and product alignment control, invert swap, and unified relative normalizer, and multiplications, alignment, inversions, and finally come with the addition part. Okay, so here the stage 2, it will align the value, okay, from the exponent alignment, okay, and also we need to add the mantissa A. Okay, so here what is the purpose of this code means, so it will be add the value and also it will multiply the value. Okay, so here normally the floating point multiplier, it will become with the exponent additions, and mantissa only we need to do for the multiplications. Okay, so here exponent addition means here the B and C, it will be added in the first alignment part. Okay, and the bias value also it will be added in the second. Okay, so alignment controller. Okay, and here only it will be come with the mantissa A. Okay, so here the mantissa A also it will be added with this addend alignment. Okay, so which means to the exponent. Okay, and mantissa B and C only it will be come with the multiplications part. Okay, and finally this alignment also it will be added in the third and fourth stage for normalizations, and final exponent value it will be taken from here. Okay, so this exponent value already we find out from the stage 1, so the exponent value here, right? So this one we have used it here, and the mantissa only it will be come with a number of process. Okay, so it will be come with the roundings, normalization, complement, LZ, EU techniques, and this product alignment controls. Okay, so addend alignment. Okay, so everything comes under the mantissa process. Okay, so then only we'll find out the output the proper way. Okay, so here depends upon the precision level, the mixed mode and multi-mode operation, and the PRA, PRM, we need to test all the conditions here. Okay, for this designs we have developed in BFLoat16 and synthesized in Xilinx Vivado, and we have simulated this work in a models and software. Okay, so now we will analyze the coding part of this work. Okay, so here this test bench of the design. Okay, so here we will be controlled the mixed precision mode and multi precision mode. Okay, also we'll initiated the precision level PRA, PRM, and EWA, EWM. Okay, so here we have assigned a different input. Okay, 001 and 010, 011. So once we select this precision select, okay, so it will be executing all the number of modes. Okay, so here this is a mode selection process. Okay, so we have a counter, as based upon the counters it will be select the precision. Okay, so 001 precision, 10 precision, 11 precision. This is for multi precision, and this is for the mixed precision process. Okay, so here this one it will become with the exponent and mantissa generations. Okay, so here initially we splitted the exponent value in 8-bit level. Okay, and then we are concatenate the value. After that we initiate the value to the architecture. Okay, so here the exponent input, and this is a mantissa input. Okay, and this is for the second operation 16-bit precision, and this is for 32-bit precision. Okay, so we can use a higher level in a 32-bit precision. Okay, and finally we analyze the value in the top model architecture. So this is a top model architectures. So here we have integrated the configuration block, FMA stage 1, stage 2, and stage 3, and stage 4. Okay, as per the architectures we have integrated the core of this paper. The FMA stage 1 it will be come with sign detector and bias generators, offset LUT, exponent alignment control, and comparators, unified LZC. Okay, and carry save adders it will be used for the paper. Okay, the same design. Okay, and finally come with a multiple precision booth multiplication technique. Okay, the same procedure for FMA stage 2 and stage 3 and stage 4, and finally we come up with this simulation. Okay, so here the mixed mode it will be select the precision level. Okay, so initial 3 stages it will become with the multi-port operations, and after that it will become with the mixed port operations. Okay, so here you can analyze the PRA and PRM and EWA, EWM. Okay, so here it will be choosing the exponent and mantissa controlling mode. So it will be start with the 00, 01, 10, and this multi-precision also it will become with the 00, 01, 10. Okay, so here it will become with the exponent input here, okay, and mantissa input, okay, and this is a 64-bit input size, okay, for ABC operation, okay, and finally the output FMA, okay, it will be taken here. This is a data output, and this is the exponent output and mantissa output, and these are the flag: overflow, underflow, and precision select and precision count. Okay, so here you can verify it, the 00, 01, 10, 00, 01, 10. Okay, so different level of the output part. Okay, and this work we have synthesized in ATIC 7 FPGA. Okay, so here this is a design summary architecture. Okay, so this design, it will be take for LUT 2463 LUT and IO equal to 331. Okay, so power it will be take with only 0.267 volt. Okay, and this is the RTL schematic for this project. Okay, so here it will become with the data ABC. So initially we given it to the configuration block, and after that we initiate the data to the FMA stage 1 and FMA stage 2 and FMA stage 3 and FMA stage 4 operations. Okay, so finally we will get a output here. Okay, so instead of this FMA stage 1, we can possible to analyze the unified LZC, carry save adder, bias generators, offset LUT, and exponent alignment control, comparators. Okay, so we initiated all the blocks and we are given priority to all the blocks here. Okay, so this one is FMA 1. Okay, and the next thing is FMA stage 2. Okay, so here it will become with the inverse swap, unified relative normalizer, product alignment control, and alignment control finalizer, added alignment, and multiplications alignment animations. Okay, so here added alignments, it will become with the alignment amount for lane 1, 2, 3, 4, and also it will become with added with the mantissa A. Okay, so this mantissa A, it will be ORed in this operation. Okay, so here we are used for the OR gate operation here. Okay, and then we take as a final output. Okay, and the final stage, it will become with the normalization, rounding, and exponent adjuster and output finalizer. Okay, that's it. And we have design abstract document. So here this is a title, base paper abstract, objective of this work, proposed abstract, existing system. Okay, so with the related nodes and disadvantages, proposed systems, and architecture descriptions. Okay, and all related nodes we attached in this work, and finally we come up with the literature survey and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research. Are you planning to publish your next innovative research in IEEE transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.